Okay, so picking up where we were last time, so I want to remind you of sort of the big strategy, right? So I've introduced this kind of weird, but ultimately we're going to find extremely powerful strategy for creating just really cool theorems, right? And it all, if you trace it back down to, what's fundamentally going on here, I claim this is really a huge part of it, right? This idea of an accumulating quantity, right? Some things, not everything, some things have this feature that the whole is the sum of the parts. And it turns out that's just tremendously important. So, in particular, if the whole is the sum of the parts, then whether that quantity actually is physical stuff or not, you can, in fact, think of it as being physical stuff. You can play make-believe, pretend that it is physical stuff, because, what would be the consequence of thinking of it as being physical stuff? Well, if it was physical stuff, I would compute the whole as being the sum of the parts, which an accumulating quantity is, right? So, it doesn't matter if it actually is physical. The point is you can pretend that it's physical because it acts like it's physical. So, go ahead, right, is the big idea. A little counterintuitive, a little uncomfortable, but a really important and valuable idea. When you have some sort of a stuff, either real physical stuff or make-believe pretend stuff, you can talk about stuff per unit size, and that gives this notion of a density, such as that. And if you have a density, then of course you can compute with an integral. And so this right here is one of our very first examples of computing with an integral, and we barely even mentioned the idea of an accumulating quantity because of course it is. Right? That's how mass works. It's just, if you have any experience in this realm that we live in, that's the nature of mass. And so, whole is the sum of the parts, and on each little part, density times size gives you stuff. So notice what we have here. It's really structurally the same argument. I'm playing this pretend. I'm doing a make-believe and pretending that this kind of abstract quantity called work that has units of energy, that is not, in fact, a concrete stuff at all in the physical sense. Yeah, but it behaves like it, so I'm going to pretend that it is, and it's all good. Right? And so that leads to, this little bit of a weird idea, but this idea of work density. A little bit strange of an idea, but it just means exactly what it sounds like. On any given little piece of area, what would I multiply by area to get the amount of work that it takes to do whatever it is that we're talking about for that little piece of area? Okay. All right. So with that in mind, and we did have to establish this arbitrary but standard notion of what we mean by an oriented boundary. Right? Very important that this is, however arbitrary, it is very standard. Got to stick with it. And with that noted, boundary circulation is an accumulating quantity. This is about where we left it last time. I gave y'all a little bit of a preview of where we're going next, but this is about where we landed. It's a bit weird. Boundary circulation doesn't feel like stuff, right? But it behaves like stuff, so you can pretend it is a stuff, and it is very valuable to pretend that it is an actual stuff. And great things happen as a consequence. So, among other things, break it up into however many pieces you want, whatever your boundary happens to be, right? I can look on as many little pieces as you like, and the whole continues to be the sum of the parts. And you can kind of see that same cancellation that made it all work on the previous page, right? The fact that this and that cancel, right? You can see that same thing happening there and there and there and there and there, and yada, yada, yada throughout. Every interior, when you cut up your hull into parts, right? Every sort of new interior edge that you create is an edge of pieces of area that are on both sides that therefore give you opposite orientations and cancel. It just always works. And again, when you have a stuff, even if it's make-believe stuff, you can talk about the corresponding density. Now, here's where I am going to sweep a couple things under the rug. There is a computation that goes to actually demonstrating the claim that I'm about to make of this new notion of density. Again, remember, circulation, we define it with a formula, right? But it behaves like a stuff. So again, you've got to remember, it's an abstract algebraic construction, but it behaves like stuff, so we are in the business of pretending that it is a stuff. And so when you have a stuff, you can talk about the density. I want to talk now about, therefore, circulation density. And again, sweeping it under the rug as to the details, it's ultimately not that bad of a calculation. It's just kind of tedious. It's just a matter of kind of writing it down and going to the trouble of doing it. It's in the book if you want to see it, right? My own personal opinion is it's not that instructive. It's important mathematically for rigor purposes. Yeah. It's not what this class is. But this is the answer, as it turns out, right? So whatever vector field you might be looking at, right? You look at these components of the vector field. There's your formula for circulation density. Okay, now I have a personal view, take, what I'm not sure what to call it, but I like to call this Green's operator, because this is the operator, the seemingly magic operator that is going to make Green's theorem work. We're about to write down Green's theorem. So it seems reasonable to me to call it Green's operator. Motivated by that, I don't want to take credit for anyone else's ideas. I think I made this up. I'm not sure. GRN, that feels like a reasonable abbreviation of green. So on a lot of my old exams, you're going to see this represented by GRN. I am not clear that I've seen it anywhere else. You probably won't see it anywhere else, but I went through a phase where I thought I was going to, make something happen, and I don't think it worked. So anyway, you'll see that on my old exams. It's more commonly called curl. There are some unfortunate aspects of calling this curl, because as y'all will recall, there is a three-dimensional curl that we talked about back in chapter 3. And it has a lot of the same interpretations and earmarks, but it is a structurally different critter. And it always made me uncomfortable using the same word to describe two things that have structural differences. So that just gave me the willies a little bit. But anyway, it is very common to call this curl, and that's just fine. It's also sometimes called rote, because if you think about where all this came from, right, we're looking literally at circulation density. Circulation, as we discussed, measures how the fluid is kind of rotating. It's measuring some sense of a rotational feature of the fluid near a given point. So, this is a pretty natural thing to call it, right? How much is that the vector field kind of rotating there in whatever sense? And there's a couple of little sort of notational curiosities, I'll call them, that are also good to know. Y'all remember this wedge product that we introduced back in chapter 1, and it turns out that this Green's operator, curl, rote, whatever you want to call it, it is del wedge. It's that's probably the most compact of these notational options, and this is very cool in that sense. It is, however, not very common use. I usually don't see this. But it's pretty cool. And then here's another one. This one I actually really don't care for. In fact, I'm going to put this one in red because I'm really uncomfortable with this. The book uses this in a couple of places. But you see how it says del cross? Okay, well here's the thing about del cross. Cross is something you do to vectors. We're already being flexible by interpreting del as a vector of sorts. But cross also is peculiar to 3 dimensions. It's 3-dimensional. This is not 3-dimensional. To make this make any sense at all, you have to imagine that there is a comma 0 that follows the P and the Q. And that's really okay, I mean, I get it, but I don't think we should be conflating 2 dimensions and 3 dimensions that brazenly. That's just my opinion. I mean, whatever, but I think that's unfortunate. And given the number of options, look at how many options we have. Do we really need option number 8? I don't think so. Right? So I'm going to really strongly discourage you from using that one. Let me discourage you from using that one also. Again, we've got so many options, right? I don't think these really justify their existence. So, just don't use those. Okay, so you got a mere 6 options for how to refer to this thing that I will call circulation density. And it's all over but the shouting. Just like work is the integral of work density and mass is the integral of mass density, well, circulation, because it is an accumulating quantity and therefore the whole is the sum of the parts, is an integral of colors. Circulation density, aka curl. And again, take your pick of which one of these many notations do you want to put in this spot. Suit yourself. And we've got ourselves a theorem. And neat stuff. And yes, we can view this as a tool for computing circulations, but we can also view it as just a general fact. Non-obvious general fact that if you have a boundary vector line integral, aka a boundary circulation, wherever it might happen to have come from, right? You can compute it as a double integral over the interior. The thing that your curve is the boundary of. Just do a double integral over that of the curl, and you win. Very surprising, super weird that this would come up, but there you go. Couple little formalities. The vector field does have to be C1, and that has to be true everywhere, and I mean everywhere. Not so much as a singularity is allowed. This is a very delicate theorem in that sense. So you do have to be careful about that, and I'll show you an example in a bit as to what can go wrong if you're not careful about that. Let's take a quick moment to recognize, just for intuition purposes, that this integrand, what does it do? Well, again, it is circulation density, and circulation is a measure of some sort of a rotation that's happening around a closed curve. And so I think this is a pretty reasonable take. What this, the way you should think about, geometrically, the way you should think about curl is that it indicates how much the fluid is rotating wherever you're evaluating this expression. Okay. All right, examples. Let's get some dirt under our fingernails here. Let's see. Let me go full page. There we go. A little bit more space. Yeah.
How does this differ from the curve we originally learned about?
The what now?
The original curve we learned about.
The original curve we learned
Curl.
about? Oh, the original curl. Oh, yeah. This is everything here is taking place in 2 dimensions. right? The original curl that we learned about back in chapter 3, that was exclusive to 3 dimensions. And you bring up a great point. I mean, again, it's like they take place in different worlds. And even worse than that, they have important distinctions in terms of what they look like and how they behave. They're really, I think it's very uncomfortable to call them both the same thing. So the fact that you asked that question is why I'm not really a huge fan of that terminology. But it's in common use, and so you just got to deal with it. Yeah. Yes.
I have a more like conceptual question. What does how much here mean? Like, how much the fluid is rotating?
I mean, some fluids are very clearly rotating. They represent, like, you remember we talked about the stirred pot, right? There is such a thing as a pot where you've stirred the heck out of it, right? And there are pots where, you just give it a little push on the side and maybe there's a gentle rotating, right? So I can't quantify this, but in some sense what we're talking about is an intuition beyond a quantification. If you want to get detailed about it, here's the details, right? The detail is that boundary circulation is a well-defined thing, and curl is boundary circulation per unit area, right? So if you want particulars, that's the particulars. What I was trying to do here is to give you some sort of hand-wavy, loosey-goosey interpretation, right? And I think this is the sort of it's not going to be perfect, right? That's the whole point of hand-wavy, loosey-goosey. Okay? But it is, roughly speaking, just kind of, in some sense, measuring in that general vicinity how much is there. If you were to drop a little leaf in that pot, how much would that leaf be rotating? Yeah. Okay. Yes.
The curl is defined at a singular point, whereas the circulation is defined for a curve.
Correct. That's right. Curl is defined at points, and circulation is defined on curves. Absolutely. Yep. Okay, let's get one under our belts. Here we go. Got a vector field given, got a curve given. Question asks us to compute the line integral. Now, notice, a couple things to notice strategically. No indication here that we should use Green's theorem. Right? It doesn't announce itself that you're supposed to use Green's theorem. So we've got to figure that out for ourselves. In fact, I'll point out further, there's no indication even that this is a circulation. We've got to sort of identify for ourselves whether that curve is or is not a closed curve. Now, it's pretty easy to tell, right? Unit circle. There's the unit circle. Does say clockwise, and that's clearly a closed curve. Okay, so because it's a closed curve, therefore it's a circulation. And now that we realize it's a circulation, now we have this on the table, or at least it seems like this is on the table that, this is a tool for computing circulations. Maybe I can use this tool. And there's another asterisk. There's another little gotcha you've got to be careful about, and this is important. Not only does it have to be a circulation, it has to be a boundary. It's right there in the name, boundary circulation. It's got to be a boundary. And boundary, you will recall, is now a loaded word. The word boundary now means oriented according to the convention. And that's the deal. This is non-negotiable, right? Arbitrary, but standard. And the theorem is made with the standard in mind, and so if you violate the standard, the theorem's not going to work. Right? So it's got to be a boundary, strictly speaking. So we've got to look at this curve and ask, is this a boundary? Does this follow our orientation convention for boundaries? And whoopsie, no it doesn't. Everybody see that? You cannot apply Green's theorem to this curve. It is not a boundary in that sense, yes.
What if both arrows pointing upwards?
Yeah, I'll get to that in a second. Yeah, but right now we're talking about, I have this awkward thing that I wanted to represent two different oriented curves on the same picture. So right now I'm talking about, right now I'm talking about the clockwise one. Yeah. Okay, not a boundary. We lose. But Cool observation. We did this once already. If you change the orientation, all that's going to do is introduce a minus sign. So let's recognize that. And the curve that we have, right, if you change its orientation, it's just going to go around the other way, which is a boundary. So this is a kind of cool opportunity. If what you have, like, oh, so close, could have been a boundary, it's just going the wrong way. Yeah, just pull this little fastening here, right? Doff the cap to recognize that, okay, granted, it's going the wrong way. Insert your minus sign accordingly, and now you got a boundary. Is that cool? Everybody on board? Okay. And now that we're computing off of a boundary, this integral here is on a boundary, and Green's theorem applies. There's Green's theorem. We're going to compute that integral. Don't forget your minus sign. Your minus sign sticks around, right? But the blue integral there, we're going to compute with Green's theorem. Double integral of curl. Okay, we've got to compute curl. We're going to compute curl by taking our P and our Q. We're going to use the little magic formula here. Right? QX minus PY. And you compute curl, and it turns out to be really convenient. Curl ends up being 2. Lucky break, right? Stuff really kind of came together there. And so now it has all come down very simply to a double integral of a constant over a barnyard variety geometric figure, and easy to compute the answer. And so look how awesome this was, right? Let's consider, what would our experience have been if we had not used Green's theorem? Well, I would have had to parameterize the circle. Here comes the sines and cosines. I would have to plug that into my vector field. Everywhere there's an x or a y, you're going to have like sines and cosines. What do you do with tangent of sine of t? Right? How do you integrate that? That's weird, right? That would be a inconvenient integral to have to wrestle with. We avoid that completely by this little argument here. Everybody cool? Powerful tools. Okay. All right, here's another example. A little bit weirder example. We have a curve that's admittedly strange curve. It's made up of line segments that start here and then go up like that, and then down here, and then over there like that, and then back down to here. Sort of a triangular figure 8, if you will. Now I want to compute the line integral over that curve, strange curve of this vector field. Okay. Whoops. Okay, is this a boundary? Well, kind of, sort of. We've got to worry about orientations. And so the observation I'm going to make here is that this curve, I can reinterpret this curve as being that plus that, right? Light blue plus dark blue. It's the same. All together, I'm going over the same paths in the same direction, so that's perfectly legal. The blue one is literally the boundary of that left triangle. The light blue one, that is. The dark blue one there, close. It's not quite exactly that boundary. It's going the wrong way. So you got to throw in a minus sign there. Sorry, I forgot to turn my ringer off. Okay. Is everybody good so far? So it all falls into place at this point. I'm computing over a curve, which is literally a sum of two other curves. So, this gives me that. And then I just recognize that this minus sign here is just going to give me a minus sign on the computation of that right half line integral, which now is explicitly a boundary, and so Green's theorem allows me to compute both of those. So I just write down Green's theorem as applied to these two literally boundary curves, because I've accounted for the minus sign. And you compute the curl, you bada bing, bada boom, it's all over but the details. And these integrals work out really conveniently. Let's see, let me try to get this all on the page. Here we go. Very easy, nice little punchline. And you might say, you know what, I feel like I could have done this without Green's theorem. And, okay, but you do 4 separate integrals. I think this is clearly easier. Is that cool? Yeah.
So I think I'm getting it. So is it like, for example, let's say that we have an ocean with a current, and then like we have a boat that moves along, like say this path. Is what we're calculating is kind of like the ocean, how much the ocean.
Well, we're calculating. I get. Let's see. Yeah, it's a little bit hard to apply the idea of what is a vector line integral in that context. You might say that since that's computing the extent to which the ocean current is moving along the curve, that you might say grand total that computes the amount that the current has assisted the boat, right? So like if let's say it's a motorboat, not a sailboat, just because we got to burn gas, and I want that to be my metaphor. If you're interested in how much gas are you saving because of the ocean currents, then I would say that's what it's computed. Yeah.
Thank you.
Yeah, sure. Yep. Okay, moving along. This is a cool little application, just kind of a twist. It's a little bit of a weird starting point, but let me just point out here at the very beginning, that's just Green's theorem. Boundary line integral is double integral of curl. It's Green's theorem as applied to this special vector field, 0, x. Now, what an odd, seemingly arbitrary choice of a very particular vector field that I want to apply Green's theorem to. But again, free country, that's what I want to do. What is so special about this vector field? Well, what's special is that its curl is 1. Now, I want to point out, it is not the only vector field whose curl is 1. There's plenty of other ones. I mean, it's not. It's easy to just write down a bunch of different vector fields where the curl is 1, right? I'm going to use this one because it kind of ends up being, I think, the most elegant. Anyway, because the curl is 1, you notice that double integral turns into literally a double integral of 1. I'm literally adding up nothing more than the areas themselves, and so of course that gives you the total area. Okay, so what we've got then, because of this clever observation, here is a line integral that will compute the area enclosed by that curve. That's weird, right? A little unexpected. I mean, you'd think if you want to compute area, you'd have to do something on the area. And what I'm saying here is now, in this case, we're going to compute the area by never going into the area at all. We're just going to go around the area, and that will compute the total area. Okay. A quick mental notational point. Don't forget that dr is just dx comma dy, right? And if you dot that out, if you use the coordinate line integral notation, then that turns into this. And it's one of the rare, not overstated, but it doesn't come up super often. But I think we have to, granted, in this case, this coordinate line integral notation is in fact more compact in this case. So it's a fairly rare circumstance where I actually like this notation in this course. Okay, further good news. Oh, I'm sorry.
So is this like mathematically defining a geometric relation between the boundary and area?
I guess you could say that. Yeah, sure. I mean, it's not the boundary itself. It's an integral computed on that boundary, a very particular integral computed on that boundary that computes the area. Yeah, absolutely. Yep. Yep. Okay, so further good news. This integral x dy, let's temporarily set aside that we're supposed to compute it on a boundary. If I just say, hey, how would I compute that on a line segment? Well, line segments are really easy to parameterize, and if you were to literally parameterize a line segment and compute the integral x dy on that line segment, it turns out it's a really easy little calculation, and this is the punchline. You get the average value of x times the change in y. And it's just details. Everyone should do that, right? Parameterize, as indicated here, parameterize a line segment from x1, y1 to x2, y2, right? Chapter 1 style, right? Just literally parameterize that line segment. T goes from 0 to 1, however you want to do it. And plug in and compute this integral straight out of the formulas. You can use this notation if you prefer to yourself. And what you will find is that you get this expression, aka x bar times delta y. So good little exercise, healthy. I encourage everybody to do that. And so the big idea then is that if you find yourself looking at a polygon and you want to compute the area of that polygon, and therefore you need to compute integral x dy on that whole boundary, just notice the boundary altogether, that boundary, a pretty ugly looking boundary, that boundary is just a sum of a bunch of individual line segments, like, well, there's the first line segment, that's L1, right? And then here's the second line segment, that's L2. And each one of these individual line segment calculations you can compute with the super easy little formula. So, for example, let's do the first one. Let's look at that edge right there. How am I going to compute this integral x dy? Well, I'm going to use the handy-dandy formula that it's x bar delta y. I'm therefore going to start by literally computing x bar and delta y. So what is the average of these x values? What's the average of 1 and 2? 1 and 12. Well, here it is. There's the average. That's x bar. And what is delta y? Well, how much did y change? Well, y went from 1 up to 6. So delta y is 5. X bar delta y, and easy arithmetic gives you what the integral is on that first edge. And just keep going around. And yeah, you got to do 9 edges, right? But, I mean, let's face it, all of this calculation here is, I'm going to say easy calculation. I mean, that's not that bad. The worst thing about that calculation is that there's some fractions for 2 in the denominator, right? It's not that bad. Pretty doable. And this computes the area for us. And now let's consider the alternative. Oh man, I guess we could kind of break this up into a bunch of little triangles like this. 7 different triangles. Annoyingly, most of these triangles are not right triangles. That means you're going to be using Heron's formula, which involves square roots. This is a pretty annoying calculation, right? If you were to take a high school geometry approach to computing this area, that would kind of stink. And your alternative, as we see here, is not that bad. Much better, yes?
I'm a little bit confused. So, like, are you saying that the line integral, like, you're finding each line lines here?
No, it's. I'm gonna say that this is. I'm gonna loosely speaking call this a magic trick. Yeah, no. Each individual line does not like. And by the way, I don't want to really pull back the curtain. There is a different take on this that I could view, but I don't. I think it's ultimately a bad road to go down, right? But each individually this calculation here, for example, that ended up with that value, that is not computing the area of this line at all. It's just that when you add all of these up over the entire boundary, that, and again, I'm gonna take the point of view magic trick. It'll compute the total area for you. It's only when you add them up it gives you the total area. Now, why does it work? Well, Green's theorem, right? It's just an immediate application of Green's theorem. So why does Green's theorem work? Well, long story about accumulating quantities in circulation. But it works. Yes?
What does a line integral represent? Not in this picture, but in general.
It represents. Now, again, it's a weird thing. It depends on how you're interpreting your vector field. If your vector field represents forces, line integrals represent work. If your vector field represents a fluid velocity, the line integral represents this weird. It's the extent to which the fluid is flowing along the curve, right? So right now we're actually thinking about either one of those interpretations. Right now we're just talking about how to compute line integrals. And, why you'd want to compute a line integral, well, yeah, okay, that depends on the particulars, but not really what we're focusing on right now. Okay, it's a cute little example. Here's another related idea, flux through a curve. Now y'all remember, I'm sure, flux, back chapter 3. Flux through a surface. Right, that we've talked about previously. This is a very, very similar idea. If you have a curve, let's say a little line segment like that, and if you've got some fluid that's flowing through as represented by a vector field, and again, for the moment, just to get the ball rolling, let's pretend like this is a constant vector field. Reasonable question to ask. To what extent is the fluid flowing through that curve? Now, why would we be interested in such a thing? Well, what kind of two-dimensional fluids do we know about, and why would we care about them? The one I think is the most fun to entertain, maybe the fluid represents like a migration of some sort of, flock-like animal, like a flock of birds, or herds of wildebeests, or whatever, right? They're kind of a fluid. Maybe, very reasonably, I want to know how many birds are flying out of some geographic region and into some other geographic region. Pretty natural. Okay, so this is a pretty reasonable thing to want to talk about, this idea of flux through a curve. Again, we're going to need to distinguish between flowing that way versus flowing that way. These are obviously opposites of each other. I want one of them to be positive and one of them to be negative. And we do that by indicating the orientation on the line segment, and we indicate that with a normal vector. That tells you which direction is the positive direction through the surface and which direction is the negative direction through the surface. You get to decide, right, in general, but when you decide, what you're doing is you're indicating which way is plus, which way is minus. Is that all cool? Yeah. Okay, well, good news. The formula works out just like the three-dimensional analog. It's exactly what you would expect. I think this is a healthy exercise as well. The way you're going to answer this, the way you're going to conclude this, you're going to look back to chapter 3. You're going to see how we did this for flux through a surface. And you're going to steal shamelessly the ideas from that calculation. You're going to adapt accordingly to it being two-dimensional instead of three-dimensional. You're basically going to rip off those ideas. This is what you'll end up with. Let me remind you, as always, these suggested exercises that I give you, if you get into trouble, don't know where to go, get stuck, come talk to me, right? This would be a fantastic question to ask in office hours. I hope someone will ask this in office hours, right? So if you get stuck, give it a try first, but then if you get stuck, ask me. Okay. Okay, so now we're going to entertain a related idea, boundary flux. Flux goes through any curve. Boundary flux means we're going to specifically think about curves that are boundaries of some two-dimensional region. We do have to make a convention. Again, there's this word boundary. I want to remind you and encourage you going forward in this class for the rest of chapters 6 and 7, when you see that word boundary, you should flinch a little bit. Right? Boundary means an oriented thing, and it has to be oriented according to the appropriate conventions, and the conventions are all standard, right? And by the way, not only are they standard, they dovetail. So it's really, if you break one of them, then you're kind of breaking all of them. It's very delicate and very particular, and again, very standard. So we do have to know what we mean when we say boundary. The rule here is outward. If you have some region and you're looking at the boundary curve and you want to know what is the orientation of boundary, well, it means outward, away from whatever region you're talking about the boundary of. Arbitrary but standard. How are we doing? A little cute observation. When we're talking about flux, our convention is outward. When we're talking about circulation, our convention is whichever way we go that puts the region on our left. Whoops, I meant to change the color there. Region on our left. And notice, now just geometric appeal. Purely geometric appeal. Here's the picture. Check it out. These are rotations of each other by 90 degrees in that order. And that always works. Just a little geometric observation. So here's another observation. For whatever it's worth, if it should ever arise, by the way, it will in a few seconds, if it should ever arise that you're looking at that normal vector dot, I'm thinking about my color choices. Here, let me change my colors here. If you're thinking about a normal vector dot some vector field, and if you consider instead the tangent vector and this thing I'm going to call F perp, which you'll notice, again, is just a 90-degree rotation, just like those are 90-degree rotations, and y'all know how to do 90-degree rotations, right? So the 90-degree counterclockwise rotation of P comma Q is minus Q comma P. If you do that, conveniently, this dot product, F dot N, and this dot product, F perp dot T, same. And how do I know that these are the same? Well, when I kind of look at the picture, these two vectors have the same magnitude. These two vectors have the same magnitude. The angle between these two is preserved when you rotate 90 degrees. So we're talking about two dot products with the same two magnitudes and the same angle. And that's how you compute dot products. Right? Magnitude times angle. And that's the same in both of these. Yep.
Could I ask what T is?
What? T, the unit tangent vector. Yeah, so that's the way we describe orientations on a curve, is a unit vector pointing in the direction that you call the positive direction on the curve. Yeah. Okay, so this is just an observation for the moment, but that having been done, here we go. Let's compute the total flux. Let me not get ahead of myself. So we're looking along, the entire boundary curve, but I'm going to chop that up into little pieces. Right? And the total flux is going to be the sum of all the little fluxes. There you go. The total over the entire boundary, add up all the little pieces. And let's see here, on each little piece, well, each little piece is approximately flat. And so on each little piece, I can use the formula from the previous page. There you go. Boom. And check it out. F dot n has showed up. And as we just established, I can rewrite that as fperp.t. So, how convenient. Right? That's why I had set that up, of course, in advance. So the reason this is useful is because now, you look at this integral, and frankly, I don't really know how to compute that integral directly. We don't have any pre-existing work that we've done of how do you compute an integral over a curve when there's an n. We haven't done anything with that before. This is unfamiliar, but notice that this is familiar. TDS. That's DR. And we've got all kinds of cool tools for how to compute line integrals of vector fields .dr. Right? We've got, we can parameterize, blah, blah, blah. So that's the big payoff there. And the particular of our several tools that I'm going to use is Green's theorem. Right? Boundary line integral. Double integral, curl. Yes?
So when you're looking at a boundary, basically the normal vector becomes the tangential vector along.
When you do that rotation like we were just talking about, but the n and the t are different, right? They're importantly different. But this little observation about when you rotate and you turn f into f perp tells us that f dot n is equal to f perp dot t. I'm not sure if I answered your question.
Yeah.
Is that okay? Yeah. Yeah, it's a clever little tricky little calculation, right? This is definitely clever. Anyway, we have a nice little punchline, and we do have to actually compute Green's operator here. And let me not take that. Let's not do that too fast and loose. Remember, we do have this formula of dq dx minus dp dy. But importantly, we're looking for the curl of. We're looking for the curl of this vector field here. And when we say dq dx minus dp dy, what we in fact mean is the x partial of the second coordinate minus the y partial of the first coordinate. Right? That formula is about how to compute the curl of p comma q. Here we're doing minus q comma p. So you do have to take that into consideration. You think about the formula for curl. This is what the curl of f perp turns into. And now it really is all over but the shouting. These minus signs sort of cancel, right? You end up with that, which you eventually notice is, oh my God, that's exactly the formula we saw back in chapter 3 for divergence. So altogether, we have ourselves another new theorem. And that is not circulation, but if you want to compute, not boundary circulation, if you want to compute boundary flux, just like Green's theorem, it is a double integral over the interior. Whatever you're talking about the boundary of. It's just that now, because we're doing flux instead of circulation, this is now divergence instead of curl. That's how it happens to turn out. Here, yeah.
Could you explain how f perp is equal to negative q comma b from?
Yeah, so that's this calculation up here. If you take this vector field there, and if you do this 90-degree rotation counterclockwise, right, then that results in what I'm calling f perp. Yeah. Yep. Okay. Alrighty. Yeah, pretty cool theorem. Now, real quick aside, for your consideration, this can also be written like that. So, again, this is just, in case you might like it. Some people like this, and there is something definitely kind of elegant about this. And if you flash back to what is wedge, this would be a good time to do that, by the way. Just go back to chapter 1 where we were talking about cross products. And one of the later, I think maybe possibly the last page of that section of notes, I introduced this thing called wedge. And you can fairly directly argue that this is what this should be. But you can also just make the observation, and this is an easy little plug and chug, that dot product is the same as wedge product with the perpendicular. And that then turns this into that. And of course, TDS is DR. Like so. So, if you like it, you don't have to. All of this wedge stuff is actually fairly uncommon. Probably won't see it very much, if at all, but is kind of cool for your consideration. Okay, so new theorem. You want to compute boundary flux. You do a double integral of divergence. This is called the two-dimensional divergence theorem. There's a three-dimensional version we'll see later. Here's a quickie example. I'm going to compute a flux. Whoa, hey, slow down. I'm going to compute a flux. This theorem doesn't say compute any flux you like. This theorem is very specifically for boundary fluxes. So we better make sure that our curve is a boundary. I'm going to try to be dramatic about all instances in which, the big theorems that we're in the process of producing, when it's really important that it be a boundary. Again, I'm going to try to make a super big deal out of this as much as I can because it's so easy to forget. Right? It's got to be a boundary. So is our curve here a boundary? Well, our curve here, unit circle, that's the boundary of the unit disk. Whoa, hey, slow down. What about orientations? Got to worry about orientations. Is this oriented the way it's supposed to? Yep, outward. That's our rule. That's our convention for boundary orientations. So this is literally a boundary. And because it's a boundary, I can cite the two-dimensional divergence theorem and plug and chug. How we doing? Cool. Here's a different take. By the way, I think it's important to see how this comes out of Green's theorem, but here's a totally independent take. I think this is actually really beautiful. If I had to pick one, frankly, I think I would have to pick this one. But boundary flux is also an accumulating quantity. And remember, that's the big point, right? All of this stuff that we're doing, the big point is look at cool stuff that you can do when you have an accumulating quantity. When the whole is the sum of the parts, boom, you have this idea. You can view it as stuff. You can talk about its density. You compute it with an integral. All you need is for it to be an accumulating quantity. And check it out, it is. Right? So looking at the whole, here's the outward oriented boundary of the whole. Here is the outward oriented boundary of the left piece. Here is the outward oriented boundary of the right piece. Now, is the whole the sum of the parts? I'm concerned about this stuff in the middle. Doesn't seem like there's any purple to match all this green and blue in the middle here. If I subtract off where the green and the blue obviously match up. Oh, my pen died, of course, at a critical moment. If I take off all this stuff where they obviously match up, there is leftover. This is our discrepancy, but check it out. It's a discrepancy where we're moving over the same edge with opposite orientations and they cancel. And so no discrepancy, and we have an accumulating quantity. And so boom, immediately immediately, as soon as you know you have an accumulating quantity, oh, okay, well, then it's a stuff. It's got a density. You can compute it with an integral. And here you go. Right? In the same way that mass is an integral of mass density, and our recent sort of initially spooky, kind of creepy, what are you talking about? Circulation is an integral of circulation density. Well, in the same way, flux is an integral of flux density. And then there, of course, is a little, calculation that has to be done, and it's important mathematically, but ultimately not as instructive as to, what is the formula and how come it's this thing that we've seen before called divergence, and that's just details, and take my word for it on that. And it's in the book, and if you want to see it, you can look in the book. I'll be happy to show you in office hours. It's just details. All right. Now this is one of my little personal pet topics. I think this is awesome. This is my way of addressing a significant concern, which is that I know that y'all are probably a little uncomfortable with a couple things I've said, such as, yeah, it's not a stuff, but you can pretend that it's stuff. It's computed on the boundary, but I'm going to imagine that it's distributed through the interior, right? That was weird. That was a weird take. And let's just go back for a moment. I'm going to flip back, way back. Not that far back. Where was it? Yeah, here we go. Right? Talking about boundary circulation being an accumulating quantity. Boundary circulation is computed on the boundary, like it says, right? Boundary circulation is computed there. Green's theorem tells me that even though it's computed on the boundary, I can imagine it as being distributed through the interior. And again, a very reasonable first reaction to that is, no it isn't. Come on. This is clearly something that's on the boundary. What do you mean I should think of it as being distributed through the interior like a sort of a stuff would be? Valid objection. Now, as I've already said, it's make-believe, right? And it's a helpful make-believe. But I want to show you a situation where not only can you see this in that way comfortably, but you already have. You guys have already comfortably digested the idea of something computed on the boundary actually accumulating over the interior. And it's change. This quantity called change. This is a single variable observation. It's going to lead us to the fundamental theorem of calculus. It's not going to be the take you've seen previously on the fundamental theorem of calculus, but if I were to draw a picture like this one, this is a graph of some function. Right? And y'all recognize the fundamental theorem of calculus. F of b minus f of a is an integral of the derivative. Right? Old news. And I claim that this f of b minus f of a change, it's computed by looking at a and b, right? That's how you compute change. If you want to know how much has f changed between here and here, yeah, you plug in the value there, you plug in the value there, and you subtract. It's computed on the boundary, entirely computed on the boundary. And now here comes my again, creepy, weird, surely you're joking request. I'm going to ask you to try to imagine that change as actually happening in the interior. And there's nothing creepy about it at all. You eventually realize, yeah, of course the function changes in the interior. I can see it changing. There's where it's changing. It's changing right along in here. There's no change happening over there. There is no change happening over there. It's right there in the picture. Is that cool? So, for your consideration, right, this is just to help the medicine go down easier. If you're uncomfortable about this idea that something computed on the boundary, that you can think of that as distributed throughout the interior, I hope this might make you more comfortable with swallowing that pill. This is very familiar. Nothing controversial about this. Accumulating quantity measured on the boundary, of course it happens in the interior. That's how stuff changes. It happens in a process. Is that cool? Is everybody on board with that? To me, this was a big eye-opener. This really helped me when I was trying to digest these ideas. I was like, oh, that isn't that weird. In fact, it's perfectly natural. So, hope that helps. Here's the other thing that I like about this comparison. And that is, if you look at the derivative in this context, let me zoom in a little bit. I can get this to behave. Right, so let's look at the derivative here. And the derivative, of course, is the slope of the tangent line, and you can think of the slope of the tangent line as the rise over the run. So there's the rise, and there's the oh gosh, hit the thing, rise over the run. Right, green over blue. That's the common interpretation we have for the derivative, rise over the run. Slope. I'm going to take a different point of view on this. Yes, I can call this the rise, but I can also recognize it as being a piece of change. This accumulating quantity, this stuff called change, and I can interpret the run as being, well, the size of a corresponding subinterval in the domain. So, rise over the run, yeah, sure. But how about this? It's change per unit size. It's stuff per unit size. It's a density. Weird take on a derivative, I know, and I know y'all are stacked with interpretations of the derivative. It's a slope. It's a speed or a velocity. It's a rate of change, right? Y'all have lots of different interpretations of the derivative. I'm not opposed to any of them. That's all good, but I want you to add a different take that's the most relevant here, and that is, please, for our purposes at this moment, try to think of the derivative as being a density, because it is. Is that cool? Again, I thought this was really helpful when I first saw this. So let's now, just to run with the metaphor, right? This example here is a deliberately weird take on what is ultimately single variable calculus, but the weird take is tailored toward this point of view that I'm trying to push. I want you to think of change as being a stuff, and I want you to think of the derivative as being its density. So, all right, looking at this interval, there is a certain amount of change that happens to this function f of x equals x squared. That's how much change, that's the total amount of this stuff called change. And where is this stuff? Right, again, I suppose you could say we compute it at the endpoints, but again, obviously that's silly. Change happens in the interior. Of course it does. So this stuff, is there more of this stuff at this point or at this point? Which one of these 2 points is there more stuff? This stuff called change. Well, the derivative is the density. The derivative is easy to compute. I can compute the value of those derivatives at these 2 points, and I see that there apparently is more of that derivative at this point, x equals 2. So grand total amount of stuff is 9, and more of it's in just this general vicinity than in that general vicinity. And if you want to, feel good about that in more familiar terms, yeah, you can literally see there is more change happening at this point than there is change happening at that point. Right there in the picture, it's steeper. Yeah? So, something to chew on. Now, I claim you could do the same thing with circulation and curl. And so, for example, I made up a semi-random, I deliberately crafted a vector field for my momentary purposes. So there's a vector field. Here's a curve, again, crafted for my purposes. And we can talk about the amount of circulation, grand total as I move around that boundary. Talk about the grand total amount of circulation. Where is it coming from? Where did that circulation actually happen? Well, first of all, let's talk about how much circulation there is. That's a negative amount of circulation along that top edge, because keep in mind, circulation is line integral. Line integral is the extent the fluid is flowing along the curve. The fluid is flowing that way. The curve is going that way. The fluid is flowing negatively along the curve. So we pick up some negative integral there. There's no circulation along in there or there because the flow is perpendicular to the curve. And there's positive circulation along in here, but I'm going to say big positive, because check it out, the field lines are longer along in here than they are along in here. So there's more positive, there's less negative. Grand total, there's a positive amount of circulation. And where is it happening? Like literally in this interior, how much, I will ask, how much of the circulation is happening in this general area? Again, sort of, counterclockwise and all that. And I say, none. And there's two different ways to see that. You can think, let's move along each of the four edges. The vector field is constant along in there, so you're going to, again, have two zeros. And you're going to have a positive and a negative, but the vector field is constant, so the positive and the negative will cancel perfectly. There is no circulation there. And physically, imagine this is the flow of water, and I put a little leaf right here. It's being pushed the same kind of on both sides, and so it's not going to rotate. There is no rotation that you would expect here as something flows downstream. Okay, what about over here? Same observation. What about over there? Same observation. What about over here? Same, exact. Yeah, because it's again constant in that general vicinity. What about here? And here we're back to, there's more positive along the bottom than there is negative along the top, because the vector field is sort of, there's a sort of gradient to the vector field as you sort of move downward. Right? You're going to find, if you were to quantify this vector field and if you were to compute the curl, you would find the curl is positive here. And that's pointing to the fact that, this rotation you're measuring on the outside boundary, that's where it's happening. Right? It's in this gray region. Just like the derivative points to where change is happening. Likewise, curl points to where circulation is happening. It's literally telling you where this boundary circulation you computed on the outside, it's literally telling you where in the interior it's coming from. Pretty cool. And you can quantify this too. I mean, by the way, likewise for divergence. Totally analogous picture. And you can just straight up compute. This computation we're about to do is a total ripoff of this calculation we just talked about here. If you want to know where the change is happening, all right, well, or not change, if you want to know where the flux is coming from or where the circulation is coming from, let's see here. You got a couple of candidate points here. And I want to know, where is there more circulation coming from? Is it the one point or is it the other point? Well, if you want to know where the circulation is coming from, you look at circulation density, which is curl, which I can compute at these two given points, and I can see where it's bigger. And it's bigger there, and so this point is where more of the circulation is coming from, more than the other. And it's harder to, draw the picture, and it's not as obviously satisfying as, in this example, it's like, well, yeah, I can literally see in the graph that there is more change happening there. And I have no such graph that I can draw in this vector field situation, but algebraically, it's telling you the same thing in the same way. Greater density, greater curl means that's where this stuff you're computing on the boundary is actually coming from. Okay, likewise for the divergence. Okay, I warned y'all about singularities. Bad things happen when you have singularities. I think it's, we really got to talk about, an example of that, just so you know what to be on the watch out for. Here's a vector field. I'm not drawing the vector field because it's a whole vector field and it'll kind of mess up my picture. But y'all kind of recognize the whole counter. There's a stirred pot here, but you see the denominator. And the closer you get to the origin, the longer these field vectors get. So this is a stirred pot. It's like a whirlpool where the closer you get to the center, it's going faster and faster. And then at the origin, it is undefined. It's what we call a singularity. Right. Well, here's the thing. This is a very special kind of a singularity. And if you take this vector field and if you compute the curl of that vector field, you will get 0, which is pretty cool, right? That's one of my favorite numbers. Certainly the easiest number to work with in a great majority of cases, right? So the curl is 0. Now, obviously not at the origin. At the origin, this thing's not even defined. But it's tempting to say, cool, the curl is 0. Double integral of the curl is therefore 0, right? I mean, how do you integrate 0? Well, it's 0. Am I going to lose my mind over a single point? Doesn't seem like that should matter at all. Okay. And if you remember, double integrals of curl by Green's theorem tell you circulation. So it kind of feels like this is saying all circulation should be 0. That, in fact, is not true. It's just not true. And in particular, we've got a theorem here that on closed curves, what you get is 2 pi times, however many times that curve loops around the origin. So, for example, if you look at this, I meant to change if you look at this curve here, that curve, k is 1, because that curve goes around the origin 1 time. And so on that green curve, this integral ends up being 2 pi. It's not 0. So the careless interpretation of Green's theorem, even because of one little singularity, gives you a wrong answer. Everybody see? This is delicate right? No singularities allowed. Now, there's some other fun things to observe about this example, and we're not going to have time to go beyond this example, so I just want to show you just kind of some other cool things. Don't forget the big idea is that circulation is a kind of a stuff, and when you compute circulation, you're really kind of adding up how much of that stuff there is on the interior. So if I go back to thinking about this curve, and if I think, well, I'm adding up the amount of stuff in the interior, where's the stuff? Well, it's not coming from where the curl is 0, because curl is density. If the density is 0, there's no stuff there. Where's the stuff? There's a total amount of 2 pi worth of stuff. Where is it? It's not, oh my gosh, what are we going to do? Well, in fact, the curl is only 0 away from the origin. And if you look at the origin, there is no curl. The curl isn't defined. Oh, that doesn't really show up very well, does it? It's not even defined. Color is going to show up here. Maybe blue show up? Kinda. Okay, let's go with blue. At the origin is the only place that stuff could have come from. Right? Again, the line integral was 2 pi. So it's a circulation. Circulation is stuff. The stuff can't be where the grain is. The stuff has to be at the origin. And so, in fact, it's like there is a discrete lump. You know, normally we think of mass as distributed, or, stuff in general we think of distributed over size, distributed over area in this case. This is like the equivalent of a point mass, except it's not a lump of mass, it's a lump of circulation. Yeah?
Is this true for any time there's a singularity?
I don't want to overstate it. There are some weirder singularity. Kind of, yeah.
So anytime there's a singularity?
I don't know. I get scared. Do you say anytime? Oh God, mathematicians get, oh my God, I'm not really quite prepared to answer that question. But usually. Okay. Yeah. It's a good way to think about it. Absolutely. So yeah, it's like there's a lump of stuff there. And by the way, this tracks with this other curve. Let's think about, just real quick. Oh, and let me maintain my little picture of, there's a lump of circulation there. What about if I look at, what if I look at this curve? Well, its interior is this region in red, and it does not include the origin. You can say this a couple different ways. You can say it as the interior does not include the origin. You can also take the point of view that, it doesn't really go around the origin. I mean, it kind of close, right? But if you're at the origin, you can escape. You can get out there, right? So grand total, it does not go around the origin. And if you compute this integral over this purple curve, you will get 0. And you can think of that as, there is no, this interior does not include that little lump of circulation. I think that's it. Okay, draw the line right here, picking up here on, today's Thursday, I guess, so tomorrow. See y'all tomorrow. Have a good one.